also has something. We are in the middle of discussing shift spaces. The full shift consists of all bi-infinite sequences using a finite alphabet, say 1 up to k. That's a compact metric space, and the shift map is a homomorphism on this compact metric space. We discussed that. And then a shift space is a closed shift invariant subset of the full shift. That's a very basic definition, and we talked a little bit about certain classes of shift spaces, like a shift of finite type. We also defined what a Sophic shift is, and the very first example was a vertex shift, which is an example of a shift of finite type. And I was starting to discuss a bit the complexity and complexity function of a shift space. The complexity function is counting how many words you can see in points in the space up to of length n. So you look at a point in X, which is a bi-infinite sequence, and then you look somewhere in that sequence, and you just look at what words of length n you can see, and you count how many there are, and that's a function of the word length that you're considering. So this is the complexity function. And I was making some claim for this complexity function. Yeah, so let's talk about that. Lemma for a shift of finite type. The complexity function either grows polynomially or exponentially. I mean, it grows polynomially includes the possibility that it doesn't grow, right? I mean, constant is a polynomial function. I only want to give you the flavor. I don't want to get lost in the details of the proof. So let me just add a second statement here, which makes this dichotomy even stronger. If X is, what did we call it? Topologically mixing vertex shift then either X is consisting of just one point, or the complexity function grows exponentially. And anyway, I'll only consider vertex shifts because we discussed this a little bit, that a shift of finite type can be recoded to become a vertex shift. Of course, the complexity function before and after recoding are different things, but I think you can figure it out. They are kind of related objects. So we suppose, for simplicity, it's not completely without loss of generality, that X equals xg is a vertex shift. For a graph G. So the graph is a general graph, but the vertex shift consists of bi-infinite paths in the graph. If the graph has a sink, meaning a vertex where you cannot go any further, where there's no outgoing edge from that sink, then you may as well just not have the sink, because bi-infinite paths cannot go there, because if the path goes there, it can't stop. It can't continue, it can't stop, because I only consider bi-infinite paths that really keep going. So we may remove sinks from the graph without changing the shift, and we also may remove sources, vertices that have no incoming edges. We may remove all sinks and vertices and sources of the graph. Possibly several times, because after you remove a sink, maybe another vertex becomes a new sink. After you remove a source, maybe another vertex becomes a new source, so you may keep having to do this. This way, we do not change X as consisting of bi-infinite paths. And may assume that any finite path in G can be extended to a bi-infinite path in G, i.e. a point in X. Why do I do that? Because we had a lemma before which said that the adjacency matrix can calculate for us how many paths there are from I to J or from J to I of length n. But we didn't say that these are actually extendable to points in the whole space. But if you remove sources and sinks, and second order sources and sinks, etc., then all finite paths can be extended, and then the complexity function can be expressed in terms of powers of the adjacency matrix. This implies that Pxn is the sum over I and j of a to the n ij. And yeah, up to bounded errors, any two norms are finite, equivalent in finite dimensions. The complexity function is just the norm of the nth power of the matrix. Up to multiplicative bounded ratios, I should maybe say, up to bounded ratios. It's asymptotic. Yeah, maybe that's the symbol I should use. They are asymptotic. Yeah, up to bounded ratios. That's what I mean. So if I don't have any extra assumptions and just aim for the general statement, I'm just asking myself what's the growth rate of the nth power of the matrix. Diagonalizing which may not work, taking shorter normal form of A over C, we obtain the first claim in the lemma. Up to a bounded ratio, you may as well diagonalize your matrix or take the shorter normal form of your matrix. So then you only need to calculate the norm of a power of a shorter normal form matrix. And that's much easier. You see that on the longer diagonal you get an exponential function, and then on the off diagonal you get the exponential function times n, and then you get an exponential function times n over 2, which is quadratic. And if the exponential function is just not existent, it's just rotation, the base is a complex number of absolute value 1, then the non-diagonal entries will be the dominant ones, will be the important ones, and otherwise I just say it has exponential growth. Yeah, so I'll stop there. And I now want to explain the last statement. So suppose now x equal xg is topological mixing. Then G is aperiodic connected. Connected and aperiodic. We had a lemma before regarding that, right? Yeah. We had a lemma, but I said precisely the opposite direction. And I didn't pay too much attention when I wrote it down, my lemma. So I'm now using the lemma in the other direction, which I didn't claim before. And in general, the other direction is not true. Topological mixing does not imply connected. But it does not imply connected precisely because of the issue that we have taken care of before. There could be sources or sinks. And sources and sinks are not visible in X, right? So if you have this graph, let's say this graph, if you have this graph, the shift space is topologically mixing, but the graph is not connected. But the graph is not connected for stupid reasons because there's a part of the graph that is not visible in the shift space. This thing doesn't have, this part of the space does not have bi-infinite paths, right? So this you need to kind of forget, which we did in the beginning of the proof. We said we'll forget sources and sinks and keep forgetting sources and sinks until there's something left that doesn't have sources and sinks. And then every path can be extended, every finite path can be extended to an infinite path. And if you just say my path consists of I'm here, the finite path consists of I'm here, so I only see one symbol, and I can extend this to a bi-infinite path. And I have a path here, then I can define open subsets in the shift space using all the extensions of this guy and all the extensions of this guy, and then topologically mixing tells me that there must be a connection between those two. There must be a way to start here and then go there. Sorry. We could have this as the converse as an exercise. I explained the gist of it, but it has this issue that you first need to get rid of sources and sinks. Okay, then the adjacency matrix A satisfies A dot n is positive in all entries, positive in all entries. Then I don't need to show the normal form. Then I just say, this is pretty easy to understand that if you have this, then powers of A to the n, which are powers of A to the n will grow exponentially. Unless something stupid happens, namely the matrix is actually a 1-by-1 matrix. And it's maybe it is a 1-by-1 matrix that has a 1, and then you're taking powers of 1, then nothing really happens, and then you're having one vertex that's connected only to itself, and that's a rather small space, and I allowed that as a possibility in my conclusion. Unless A is a 1-by-1 matrix, powers of B equals A to the n will grow exponentially. B is probably much bigger, but if you just think of the matrix consisting of ones, B is bigger in every entry than 1, 1, 1, 1, 1, 1, 1, 1, 1. And if you take powers of that guy, I think you can figure it out that this grows exponentially. As long as there are at least 2 columns and rows. Said differently, this matrix is the adjacency matrix that defines the full shift. And the full shift has an exponential number of words. There are no constraints. And yeah, maybe this B is not that matrix, but B is bigger than that matrix. But maybe the growth rate is a bit slower because B is actually a power of A, and you need to convert that back into a statement for A. But I'll leave it at that. Sorry, that was a bit impressionistic. But I hope it's clear enough what's going on. All I wanted to say with this lemma is that the complexity function is usually big in a shift of finite type. If I have some kind of irreducibility assumption, connectedness assumption in my graph, then the complexity function will grow exponentially, unless the space is rather small. And one could be interested in studying what's the smallest complexity that you could have for a shift space. And that's the theorem of Morse and Hedlund that we want to prove now. And yeah, it's a nice, easy statement, and the proof will also be very easy. Let X be a shift space, not of finite type, not necessarily of finite type. Then X is finite if and only if there exists sum n in n, so that the complexity function of the shift space at n is less or equal than n. One direction is not worth talking about much. If your shift space is finite, then you will only see finitely many words. So of course, for some n, px of n will be bounded by n. So this is obvious. If your shift is finite, your complexity function is bounded. So we are interested in the other direction. We suppose px of n is less or equal than n. Note that px of n minus 1 is less or equal than px of n. I'm not writing it down, but why is that true? I said that this complexity function tells you how many different words you see anywhere in the sequence, anywhere in the space, right? But anywhere in the sequence, you actually don't have to look. You can also just look at the digits, the symbols you see from 1 to n at a fixed window. Because the shift space contains all shifts of your sequence anyway. So this is the cardinality of the projection to 1 up to n applied to the full space. And this is the projection up to from 1 up to n minus 1. So what I'm saying is that the words you have of length n minus 1, you can all obtain, all of them you can obtain by just taking the words of length n and forgetting the last symbol. So that follows from the definition of the complexity function and the fact that your shift space is invariant on the shift. Okay? Maybe this is smaller. Maybe the px n minus 1 is smaller than the px of n, but it can't be bigger. And this allows us to sort of find a minimal n for which px of n is less or equal than n. And for this minimal n, let n be minimal with px of n is less or equal than n. If n is equal to 1, then px of n, px of 1 is equal to 1, and the cardinality of x is 1. Because what does it mean to have px of 1 equals 1? That means that you only have one symbol. Everywhere in the space, you just see one symbol. But then you only have a fixed point consisting of that one symbol. So if this minimal n with px of n less or equal than 1, less or equal than n, is that minimal n is 1, px of 1 can't be 0. There must be at least one symbol because our spaces are never empty. Right? We agreed on at some point that our dynamical systems are not the empty set. So px of 1 equals 0 is not an option. Px of 1 equals 1 is an option, but that means we only have one symbol, and then the whole space consists of one bi-infinite sequence. So suppose n is bigger than 1, then px of n minus 1 is bigger than n minus 1, right? Because n is minimal. That we have chosen the minimal n with this inequality, so the number that's one smaller must be bigger than n minus 1. But it's also less or equal than px of n, which is less or equal than n. Right? Because of this observation up here. So, yeah, this shows that px of n minus 1 is equal to px of n is equal to n. So we have n words of length n, but we also have n words of length n minus 1. That's what we are saying here. Yeah, let W1 up to Wn be the language of length n. So that's the projection of the whole space onto the coordinates 1 up to n. Those are the words that I can see that are of length n. I now define two maps, namely the map that forgets the rightmost symbol, which I call L because it gives me the left part of the thing. We define L from Ln to Ln minus 1 by forgetting the rightmost symbol, and R from Ln to Ln minus 1 by forgetting the first symbol. This implies that L of Ln equals R of Ln equals Ln minus 1. Why? It's again somehow what we said here, that if you project the bi-infinite sequence to the first n coordinates, and then project to the first n minus 1 coordinates, that's the map L, you obtain all possibilities, because the original space is shift invariant. So if you want to obtain a certain, well, just by definition. But for R, we use that it's shift invariant. Because for R, we have some sequence in Ln minus 1 that could be obtained from a bi-infinite sequence in X by projecting to the coordinates 1 up to n minus 1. Take that point and shift it once, so that that word that we're interested in is now at coordinates 2 up to n. Project to coordinates 1 up to n, then you have an element from Ln. And now forget the first symbol, then you have the sequence that you wanted. So that gives you the search activity. Okay? So Ln has n points. Ln minus 1 has n points, and L and R are both onto. Okay, so then they're injective as well. So L and R are bijections from Ln to Ln minus 1. And if you think about what that means is, it means that if you take a word in Ln minus 1, there's only one way to extend it to the left or to extend it to the right, to a word that still could exist in X. So that means the n minus 1 consecutive symbols determine the whole point. So capital X has n points. It's sort of in this statement, but I'll write it down. Equivalently, this shows that L and R are both projections. Hence, given some W in L n minus 1, there is only one way of adding a symbol to the right or to the left to obtain a word in Ln. So let me draw it. So we have here this word W in Ln minus 1. And then there's only one possibility to write here a symbol AN, so that this is in Ln. This was in Ln minus 1, and this is in an element from my alphabet. This is unique. So it exists, but it's unique. Now you look at the word, the n minus 1 word you created sort of on the right here. Look at this part and say this is a word in Ln minus 1, and there's only one possible symbol on the right that I can put. So there exists again an AN minus 1, and then there exists an AN minus 2, and so on. And these are uniquely determined. If I write down something else, then I create a word of length n that is not appearing in my shift space. And the same applies here. I use the map L, that L is bijection, because L forgets a symbol on the right, and this forgetting is not forgetting anything. And by using that R is also a bijection, I can create an A0 here on the left, also uniquely determined, and an A minus 1, etc., etc. And then this, I'll create a point that could be an X, and it has to be an X. And because if this point is missing, then this word that I started with could not possibly be a word in my shift space. Anyway, all I want to show is that X is finite, and I get this. For iterating this, we obtain for every W in Ln minus 1 uniquely determined X in X projecting to X, projecting to it. Hence, X is equal to Ln minus 1 is equal to n. It's finite, and we're happy. Yeah, and every time something like that happens, there's some bound. People are interested in whether that bound could be improved. Maybe there's some more clever argument. I mean, here we really just use pigeonhole principle. It's just, there wasn't much of mathematics used to prove that statement here. So you could argue maybe because it was such a basic observation that the truth could be better than this. And you could ask that, but people found out that no, there is actually an infinite shift space where the complexity function is just one bigger for every n than this upper bound. And those are maybe those shift spaces are interesting because they are the smallest they could possibly be in terms of the complexity function without being finite. And it's sequences with this property, and hence maybe also the shift spaces with this property are called Sturmian. Definition, X is Sturmian if the complexity function is n plus 1 for all n and n. And I wanted to give you an example. Okay, I can give you a stupid example. I think if you take the vertex shift for that graph and you do a short calculation, you see that it satisfies this n plus 1 thing. But it's a stupid example because it's like our north-south dynamics. There's a south point, which is a fixed point, and you can move from the south pole to the north pole, but you can only do it once. It's not the most interesting dynamical system, so maybe this is example 0, and we don't want to think about that one so much. And the other example is more interesting. It's sort of created by circle rotation. And you could argue circle rotations are also very, very much not complicated dynamically speaking, but they are more complicated than north-south dynamics. And from that perspective, it's not a surprise that you can use the circle rotation to create the least complicated shift space that possibly could exist. Let alpha be not a rational number. We define R alpha, as we always do. R alpha maps X in the torus to X plus alpha mod 1 in the torus. So it's the circle rotation. And two intervals. We define this map, and two intervals. Let's say J1 is the interval from from 0 to 1 minus alpha, and J2 is the interval from 1 minus alpha to 1. Modulo 1, both, mod 1, as subsets of the torus. So let me just draw it. I have my circle, somewhere I have 0, maybe I have 0 here. And then I'll go sort of from 0 to minus alpha or to 1 minus alpha, depending on whether you want to write the 1 or not. It's not relevant, mod 1. And then there are two intervals. There's the first one, which is this one, J1, and then there's the second one, which is J2. And the 1 and the 2 will be my two symbols that I want to use in the Sturmian sequence. And now I will define you, in some sense, I will define you the language of the shift space, and then when I've defined the language, we will know what the shift space is. Meaning I will tell you which words are allowed in the symbols 1 up to n, in the symbols 1 and 2 of length n. Okay, and I use the dynamics of R alpha to tell you which symbols are allowed, which words are allowed. We call a word W, 1, 2, length n, allowed if I take my J and I use the indices, I use the coordinates of W as indices of my intervals. So I take JW1 and then JW2 dot 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 JWN. I want to use those but of course I also want to use the rotation to somehow do stuff with the intervals, and I want to ask whether that intersection that I get is non-zero. And what do I do is I take the pre-image of the second one under R alpha, keep intersecting, and then of the last interval I take the pre-image under n minus 1. And maybe I call this JW. So I want this JW to be a non-empty interval. Yeah, I already made a claim. I claim that these JWs are intervals. And not only do I claim that the JWs are non-empty intervals, I also claim that there are precisely n plus 1 of them that are non-empty. And then I have precisely n plus 1 allowed words, because my word is allowed if the interval is non-empty. So if I check that I have precisely n plus 1 such intervals, then I have n plus 1 allowed words. And if I use these words to define a shift space, then the shift space will be Sturmian. But we do that after the break. Since when do we have the dong? Welcome back. I just got a couple of questions in the break. Question 1, I remember, was, is it allowed to assume that X is a compact metric in the exercise series? The answer is it depends on the context. Currently, the exercise series is about topological dynamics, so there the answer should be yes, you can assume that. And maybe it can be made a bit more clear in the future version of the exercise series. Same with continuity. I mean, if you're talking about topological dynamics, we want a compact metric space, we want a continuous transformation. There was also a question to how much of that is sort of necessary. Is compact, I think, is really important because you can very quickly destroy all the theorems if you don't have compactness. Metric is less important, but it's very convenient. If you want to invest energy into losing the assumption metric, it's possible to do that. There's research in that direction, and depending on the context, that research might also be interesting. But depending on what you want to do, and I think I want to go in a different direction, it's maybe also not so interesting. It's sort of a red herring of sorts. Sort of a question about mathematical taste, not more than about whether it makes sense. And then there was another comment. There exists a forum, I didn't mention that before, and some questions and some discussions there are very welcome. And I think Segev and Konstantin and Veyun and maybe also our teaching assistants will monitor that forum a bit and will help you with questions if you have questions. Good. Right, we want to talk about this example of a Sturmian space. I defined the words. Of course, I changed my signs from the notes here because I thought they are better. I might screw up now, but let's be positive. So I want to claim the following. There are precisely n plus 1 allowed words of length n. The corresponding sets JW are half open intervals the endpoints of these intervals are precisely 0 minus alpha. Now I'm forgetting the 1 because there will be other mod 1s appearing, other integers that are appearing that I don't know that depend on alpha, so I don't write them down. Minus 2 alpha up to minus n alpha. And maybe you see that these are n plus 1 points. These n plus 1 points lie somewhere in the circle. I don't know in which order they'll end up in. I don't care. And these n plus 1 points chop the circle precisely into n plus 1 intervals. And those JWs are precisely the n plus 1 intervals that are created by these n plus 1 points. Yeah. And of course, the purpose of these extra statements are so that the induction kind of makes sense. It's sometimes the case that you prove a stronger statement in the induction than you care about, just so that the inductive step makes more sense. And here we added this geometry to the thing we care about. We wanted precisely these n plus 1 points, n plus 1 allowed words, but if they correspond to these intervals and these intervals have these endpoints, then maybe we are more interested in these, So for n equals 1, the claim holds. Right? There are 2 allowed symbols because the 2 intervals are not empty. and the endpoints of the two interval are 0, which is the same as 1, and 1 minus alpha, which is the same as minus alpha. So we now assume the game holds for n. Let W be an allowed word. With endpoints let me just write JW equals the interval at some AB, some half-open interval AB inside the torus, mod 1. You could worry about the circle being sort of connected, being a circle, right? That on the right you keep going and you end up again entering the interval on the left. But my very first intervals don't do that, right? My very first interval is J1 and J2. The first one stops before it reaches 1, and the other one stops precisely at 1. So the J1 and the J2 don't stretch across the 0 is equal to 1 border. Hence, the JWs don't stretch across the 0 equals 1 border. So this might be 0, this might be 1, but these are numbers between 0 and 1. 0 less or equal than A, less than B, less or equal than 1. Note that I take my R alpha to the minus n of J1. That's now the interval from minus n alpha to minus n plus 1 alpha, kind of. But this guy could sort of stretch across 0 is equal to 1. So it's a slightly confusing thing to think about. I wanted to avoid it, but yeah, let's do something else. Let's look at R alpha to the minus 1 of JW. This is now, no, let me forget the whole pre-image discussion and talk about it in a slightly different way, and hopefully then it's easier to avoid this 0 equals 1 nuisance. Note JW is equal to all the points x in the torus for which W describes the locations of R alpha to the J of x for J equals 0 to n minus 1 with respect to capital J1 or capital J2, right? By which I mean that the W tells me in which interval of the two intervals I am at for the times between 0 and n minus 1. That's very much the definition of my JW that I've given up there. Okay? And I want to understand what happens if I now add one more time unit to my description, right? So I want to extend the W sort of to a word of length m plus 1 and ask myself, in which ways is it possible? Can I do this with symbol 1 or with symbol 2 or maybe both? The question of how the allowed word W extends corresponds to the question if JW equals JWA, or it's contains JWA for A in 0 and 1 or 2, right? We add symbol 1, 2, and we want to know what 1 or 2 to the word, want to know whether that's possible. If n plus 1 alpha is not in JW, that's always mod 1. Then JW is equal to JWA for some A in 1, 2. Let's try to understand that claim. Why is that true? Okay, so that's sort of an important step in the induction. Let's mark it with something, star, and then let's make a second claim, pentagon, if n plus 1 alpha is in JW, then W extends in 2 ways. To allowed words. So those two claims together will do what I want. You have a question?
Sorry, why is there a question with respect to the inclusion? Isn't the inclusion always true?
Yeah, sure. Yes, it's always true, but yeah, the question, I guess, is precisely whether maybe that's the question. Yeah, the question is whether it's included but not equal. Yes. Now it makes more sense. Thank you. I bought some nice chocolate, so it was a useful comment. Sorry. Those are the things that are obvious at some point, and then when you are at the blackboard, they become a bit less obvious or less clear how to write it down. The thing is, the gist of it, after one understands it, is that when we take our original interval and rotate it by the nth power, both of the two intervals, we rotate both of the two intervals by the nth power of our R alpha. We used to have the endpoints 0 and minus alpha, just 2 endpoints. And now we shift them by minus n alpha, because we want to add here another intersection with an interval. So we shift them. One of the endpoints was 0, shifted, it becomes n alpha. but n alpha was already an endpoint in the JW list, in the list of allowed words of length n. Because I used alpha twice. I used alpha in the definition of my endpoints of the J's and in the definition of my rotation map. If I had just done my J's is a division into two intervals, it will have two endpoints, and the rotated ones will be two endpoints and will maybe be in general position with the previous endpoints that I had, and then I might have two n endpoints. So much faster growth of possible endpoints in the picture. But because I had used in my J1 and J2 the endpoints 0 and minus alpha, when I have already the previous claim that the JWs of length n have endpoints between 0 and minus n alpha, when I now take the original intervals and shift them by minus n, apply minus n alpha to them, my endpoints are two of them, but one of them I already have as an endpoint in the old list. So only this extra endpoint, n plus 1 alpha, this extra endpoint has the potential, will split one of the old allowed intervals into two intervals. So this happens once, and for all other guys, the next symbol is determined because my interval is contained in an interval where a symbol is added. Which symbol is determined by alpha? I don't know. Since this was meant as an easy example of something, I think I'll leave it at that. Shouldn't be so difficult, but I get currently confused with the exponents and everything. So thank you. Good, so we return to something easier, less confusing, namely some theory, and we start ergodic theory. So I said before, if you're talking about topological dynamics and some example asks you to prove something about t goes from x to x, then here presumably you want to assume that x is a compact metric space and t is at least continuous, maybe a homomorphism. But now we are changing sort of category. We are talking about a different setup. So in the next exercise sheet, the question, what is the x, is much more interesting because it could be an example for the old problem, old theory, or it could be an example to the new theory that we're starting today. And now the x has less structure in some sense. And simultaneously, we want to prove stronger theorems, which is confusing. But we are going into measure theory, and we want to prove stronger theorems for almost every point. And that makes it easier. Good, so that's ergodic theory. In the following, let X be a measurable space i.e. X is a set and B is a sigma algebra on X. So it's a subset of the power set of X. Moreover, let mu be a probability measure on xb, so that's a function that's defined not on all sets, but only on the sigma algebra. And on the sigma algebra, it has all the nice properties that we learned in measure theory. So most importantly, of course, it's countably additive. So if you can write a set, if you do write a set in B as a countable disjoint union of sets in B, then the measure of the union equals the sum of the measures of the original sets. So you have, learned that in your past. That's definitely an assumption. We can't build up the Lebesgue integration theory here. Right, and then we also know what measurable means. And we now want to study not just measurable maps, we want to study measure-preserving maps. Definition, let X be mu, be a probability space, meaning precisely that we have a measurable space with a probability measure on it. Let T from X to X be measurable. Then T is called measure preserving. Or mu is called T invariant. They mean the same thing. If mu of T inverse of B is equal mu of B for every B in B. So the pre-image of every measurable set has the same measure as the original set. That's the natural thing to talk about the pre-images, because that's also how measurable is defined, if you recall it. Measurability of maps is defined using pre-images, because that has the most natural behavior under unions and intersections, etc., etc. So, of course, we stick to the same principle and hence make this definition. Why are there two names to it? Because it depends on the focus. Sometimes you first of all interested in fixing the transformation and then asking about measures. And then the measure would be called T invariant. But sometimes the measure is quite natural and it's given to you before you start thinking about the maps. And then the map would be called measure preserving. But it means the same thing. It means precisely this formula. Maybe some general aspect is that if T from XB to YC, YC is another measurable space, is measurable, and mu is a measure on X, then T star mu is a measure, is the push forward measure on Y, and the push forward measure on Y is defined really precisely by this formula here. So T star mu of a set C will be equal to mu of T inverse of C for C in C. Takes a little bit getting used to. Sets always go backwards. Sets you have to take pre-images of. Measures go forwards. Measures are like points. So the push forward of a measure is really, again, a measure on the image space. So it goes like points would go. But sets, you always take pre-images, because that's the thing that you know makes sense, gives you measurable sets. You should think of as a measure as a convex combination of points or a quantum state of points, right? I mean, that's what the measure is. So then it's not surprising that the measure goes naturally forward, even though sets go backwards. Implicitly, I'm saying that there's no natural definition of a pullback measure. It's not. Maybe your transformation is invertible, then of course it's just a special case of the push forward. But I'm not saying that it can't be done, but it's not natural, and maybe you have to apply some axiom of choice to lift your measure from the quotient to a measure on the space. That may as well exist and might be useful at times, but it's not a natural thing that you write down in one easy formula and has canonical good properties. But the push forward has canonical good properties, so let me just give you one of them. Lemma, if f is, say, greater or equal 0 on measurable on y, then you can integrate f with respect to the push forward measure. I mean, positive functions can always be integrated with respect to any measure you want, right? No questions asked. It might be infinite, but it makes sense. And then what you also could do is you could say, but actually I can create a function on x very easily using the transformation that goes from x to y by just taking the composition of f with t and then integrating the new function over x with respect to mu. They're the same thing. And of course, if you know this lemma, if you have proven this lemma, I invite you to think about this lemma. Then you have similar formula for a measure preserving map. I don't write it down because it's kind of measure theory. It's a short exercise in measure theory, but let's talk about it. Why should it be true? Yes?
I assume f takes values in the real numbers, right?
Yes, it's greater or equal 0, yes.
Exactly. So we equip those with the real sigma algebra?
We don't need the sigma algebra on the reals, we don't need it.
Sorry, we use the push forward measure, my bad. Yeah.
Y and x have their own sigma algebras, yes.
Okay, sorry.
I mean, what do you do in measure theory all the time? Yes?
Well, we could prove it for simple functions.
Yes,
in the relation
thank you. So let's stop for a moment. The first suggestion was, let's take maybe an even simpler suggestion than your suggestion is, let's take look at the characteristic function of a set. And then you unfold the definition left-right, and you just see the definition of the push forward. So this is a check because of the definition. And then we could do simple functions. Simple functions are linear combinations of characteristic functions, positive linear combinations, say, for the moment. But left and right are both linear expressions. So if you take a linear combination with positive coefficients of characteristic functions, it will also be true. Sorry? And then?
And then we can use pretty famous result on these kinds of functions.
Yeah.
Yeah, of the sequence of simple functions that go upwards to.
Yeah, right. So monotone convergence is the key word. Any measurable positive valued function you can write as the increasing limit of a sequence of simple functions, and then you apply monotone convergence left and right. You know along the sequence it's true. Monotone convergence tells you that the integral and limits commute, and you get the statement for f greater equals 0 measurable as claimed. Thank you. f greater equals 0 using monotone convergence. But I have 10 minutes, so let's prove something more interesting. Theorem. Poincare recurrence. Let T from X be mu, be measure preserving on a probability space. Let E in X be measurable. Then, those are the assumptions, pretty minimal assumptions. Then for mu, almost every X in E, there exists infinitely many returns to E. There exists nk going to infinity, so that, of course, depending on x, so the t to the nk of x is again in the set E. If something happened at time 0, it's going to happen infinitely many times in the future. Or your point is negligible. If that's not true, then you were very unlucky with the choice of your base point. I should maybe emphasize that the assumption that our measure is a probability measure is kind of the replacement of the compactness assumption we had been working with in the topological dynamics. So same as back then, if you are thinking about dropping that assumption, don't. Everything goes bad. This theorem is complete nonsense if you would not have a probability space. Just think again about translation on the reals. It will preserve the measure, no questions asked, H measure, the back measure, but there will be no recurrence. There is a theory of an infinite ergodic theory exists, but the possibility of dissipative action, sort of action that sort of has this north-south wandering sets kind of thing, is always a possibility in infinite ergodic theory. And first we want to learn about, definitely about the standard setting of a probability space. Okay, proof. It's a nice theorem, very general and very useful. You could argue that it's kind of a pigeonhole principle within a ergodic theorem. And the proof, yeah, anyway. Proof isn't hard. We define AM to be the union over n greater equal m t to the minus ne. It's measurable. It's defined by preimages and unions. It's definitely measurable. It consists of all the points x and x for which x has a visit to E at time m or later. Right? So that's kind of a nice set that relates to the thing we are trying to talk about. Okay, so that's a nice set. Let's define another nice set. And A equal the intersection over all m from 0 to infinity of am, which consists of all points with infinitely many visits to E. Because no matter how late I want to visit, I will be a visit to E in this set, if I'm in the set. X in X, X has infinitely many visits to E. What I want to show is that E is in A, right? Maybe not completely. I want to show that whatever is in E but not in A has measure 0. Then I have proved the theorem. So I'm interested in measures of these sets. So for instance, note E is in A0. Right? That is clear. I didn't say what M is. M could be 0. Maybe it's not allowed to be negative. I don't know what T of E is. T of E might not be measurable if I'm only given a measurable map without knowing that the inverse exists and is measurable. But M equals 0 and T to the 0, that makes sense. E is in A0. A0 is containing A1, is containing A2, is containing, etc., etc. Okay. And then there's another thing that's staring also in our face. And after that, everything is trivial. The pre-image of A to the AM is AM plus 1. Because if I take the pre-image, the pre-images have good properties with respect to unions. I emphasized that before, right? So I can take this pre-image, put it here, and that just increases the exponent. And then I have T inverse of AM is AM plus 1. But pre-images are supposed to have the same measure, so these two things have the same measure. Mu of AM is mu of AM plus 1. So a pre-image of A0 is A1, they have the same measure, but A1 is a subset of A0. So what's missing between the two sets is a null set. What's missing between those two sets is a null set, etc., etc., etc. So taking the countable union of these null sets, A is actually A0, apart from this null set. This implies that mu of AM without AM plus 1 is 0, and also mu of A without A0 is equal to 0. Together with E is contained in A0, we obtain the theorem. Yeah, I had one more page. So what I find also kind of nice is that Poincare recurrence immediately implies the recurrence theorem that we had in the topological dynamics, assuming you have an invariant probability measure on a compact metric space. Assuming you have an invariant probability measure on a compact metric space, almost every point with respect to your probability measure will be recurrent in the sense of the theorem that we had before. So if you can show the existence of an invariant measure, which we will be able to show, this provides a different proof which uses the axiom of choice in a different place, better hidden place than our previous proof did. Okay, you had a question?
Isn't A without A0 always the empty set?
The other way around, maybe, yeah. Thank you. A is smaller, so we take A0 without A. Thank you. Oh, sorry. Yes. I mean, there's this chain of smaller for all the things, and then A is the infinite intersection of all of them. And to know what's A0 without A, I need to take the unions of A0 without A1, of A1 without A0, and so on. I take all these unions, but each one of these sets is a null set. So I get that A0 modulo the measure is the same thing as A. And E is an A0, so I'm done. Yes.
So
Yes.
I guess this is the step where we use the fact that mu is a probability measure.
Yeah. So, yeah. If this measure is finite and equal, then we know that the complement must be a null set.
Yeah.
But if the measure would be infinite,
Yeah.
we might still be missing a set of measure 1, right? And then when we take the union, it's a set of infinite measure that's different. Yeah. Thank you. See you tomorrow.